The speed of light is the universal speed limit. Nothing can travel faster than the speed of light, not even information. But why can't anything travel faster than light? What's so special about light? Stay tuned and you'll find out. Calling the universal speed limit the speed of light is a bit of a misnomer. While light does travel at this speed in a vacuum, it's not just light that travels at this speed, but also gravitational waves. In fact, light doesn't even always travel at this speed, but actually travels at a slower speed when it is passing through a medium. The speed of light inside a medium such as glass or water can be exceeded because it is slower than the universal speed limit. What is actually meant by the term the speed of light is the maximum speed at which the effects of an event can propagate through the universe, or in other words, the speed of causality. But how are we so sure this is the maximum speed at which effects can propagate through the universe? We actually came to this conclusion through a failed experiment. Before we get to the experiment, let's consider a hypothetical scenario. Imagine you are on a train that is waiting at a station. Let's say you shine a torch towards a mirror at the front of the train and time how long it takes for the light to make a round trip. After you've taken this measurement, the train starts moving at a speed close to the speed of light. How long will it take for the light to make a round trip now that the train is moving? Then imagine you are outside the train observing somebody doing this experiment inside the moving train. What result are you going to observe now? The first possibility is that the speed at which light travels is not affected by the motion of the train. This means the light will now take significantly longer to make the round trip since the mirror is moving away from the light. In this scenario, light is traveling at exactly the same speed both inside and outside the train. The second possibility is that the round trip time is not affected by the motion of the train. This means you will record the same round trip time when the train is moving that you recorded when the train wasn't moving. This also means that light is traveling at a higher speed inside the train. By the late 19th century, it had already been established that the speed of light is the same regardless of whether a light source is moving or stationary. This rules out the second possibility. To explain the behavior of light, it was postulated that the universe is filled with a substance called the luminiferous ether through which light waves propagate. According to this model, the time it takes for light to make a round trip between 2 points increases when the 2 points are moving in the same direction as the light. Intuitively, this is what we would expect, because this is how sound and water waves behave. Thus, the first possible scenario is what we should observe in real life. The Michelson-Morley experiment was devised by Albert Michelson and Edward Morley to test this hypothesis. The aim was to prove the existence of the ether by measuring how fast the Earth is moving through it. The experimental setup involves a beam splitter that splits a beam of light into 2 perpendicular paths. There is a mirror at the end of each path that returns the light back to the beam splitter, which reconverges the 2 beams. By analyzing the interference pattern that forms, the difference in the round-trip times of the 2 paths is determined. One of the paths is oriented along the direction in which the Earth is moving. If the ether hypothesis is true, light should take a longer time to complete a round trip in this path than the other path. However, the results were perplexing. There was no observable difference in the round-trip times between the 2 paths. Thus, the experiment failed to prove the existence of the ether. This result, and the results of other similar experiments, also rules out the first possibility of our hypothetical train scenario. In real life, we should actually observe the same round-trip time both when the train is moving and when it is stationary. But how is this possible? The speed of light inside the moving train has to match that of light emitted from stationary light sources, but that should also result in a longer round-trip time being measured. It turns out we've actually made a few false assumptions. We've assumed that the clock inside the moving train is ticking at the same rate as a stationary clock. In reality, the moving clock is actually ticking at a slower rate compared to a stationary clock, or in other words, time slows down when the train is moving. This is called time dilation. The faster you are moving, the more time slows down. Because the clock on board the train is ticking at a slower rate, the same round-trip time is measured when the train is moving. We also assume that the distance between the torch and the mirror is the same both when the train is moving and when the train is stationary. However, this distance is actually shorter when the train is moving. In fact, the entire train appears contracted when viewed by a stationary observer. This is called length contraction. The faster the train is moving, the more it is contracted. Because of length contraction, light is actually traveling over a shorter distance when the train is moving, thus reducing the round-trip time to the same time that is measured when the train is stationary. It is important to note that time dilation and length contraction are not perceivable when you are moving with the train. From this frame of reference, the train is stationary, time flows at a normal rate, and distances are not contracted. Instead, it is the outside world that appears to be moving while experiencing time dilation and length contraction. It is actually impossible to tell which frame of reference is true and which frame of reference is just an illusion. As a result, both frames of reference are considered equally valid and true. Time dilation and length contraction are collectively known as the Lorentz transformations, which were developed by Hendrik Lorentz and later refined by Henri Poincaré. The Lorentz transformations form the basis of the theory of special relativity that was formulated by Albert Einstein in 1905. So, why is it impossible to travel faster than the speed of light? Let's get back to the train and imagine that its speed increases every second by 1% the speed of light. Ignoring all practical limitations, surely the speed of the train will exceed the speed of light eventually. Actually, it won't. To see why, let's look at the train from the frame of reference of the stationary observer. Whenever the velocity of the train increases, the train becomes shorter due to length contraction. This means the amount by which the train is accelerating, in this frame of reference, actually decreases over time. In order for the train to reach the speed of light, it will have to keep accelerating for an infinite amount of time. Alternatively, it will have to accelerate by an infinite amount in a finite amount of time. From the train's frame of reference, no matter how much it accelerates, light will always be moving away from it at the same speed. In both cases, it is impossible for the train to even reach the speed of light, let alone exceed it. This limit doesn't just apply to our hypothetical train, but also applies to everything that has mass. Moreover, the speed of light isn't just a speed limit for objects with mass, but also a limit to how fast information can be sent through space. To see why, let's imagine a scenario where information travels faster than the speed of light and see what happens. Imagine a planet orbiting a sun. Now imagine that the sun suddenly disappears. What's going to happen to the planet? According to Newtonian mechanics, gravity acts instantaneously over a distance. This means when the sun disappears, the planet will instantaneously leave its orbit and fly out into space. If you are somewhere near the sun, you will first see the sun disappear, and only then will you see the planet leave its orbit. However, if you were in a spaceship moving towards the planet at constant velocity, you will first see the planet leaving its orbit, and only then, after a delay, will you see the sun disappear. In this frame of reference, you've observed the effects of the sun's disappearance happening before the cause. This is a problem because both frames of reference are equally valid accounts of reality, and neither is more true than the other. If faster than light travel is possible, the relationship between cause and effect breaks down. An effect may, and should in some frames of reference, happen before its cause. Since our observations always show effects following their cause, we can deduce that it is impossible for any form of information to be sent faster than the speed of light. Now, let's get back to the thought experiment, but this time imagine that the planet doesn't leave its orbit as soon as the sun disappears. Instead, the disappearance of the sun's gravity is only felt when the last light from the sun reaches the planet. If you are standing near the sun, nothing changes. You still see the sun disappearing before the planet leaves its orbit. However, if you are moving towards the planet, you will not see the planet leaving its orbit first, since the effect of the sun disappearing hasn't reached the planet yet. Instead, you will only see the planet leaving its orbit after you have already seen the Sun disappearing. The effect now follows the cause in all frames of reference. So, not only is it impossible to accelerate to the speed of light, but breaking the universal speed limit also breaks causality as we know it. Thank you for watching, and I hope you enjoyed it. This video was sponsored by TableQuest, a table reservation and pre-order management system for restaurants.